This is Mr. Champlin. We are going to be looking at Chapter 1 in the Knight textbook on concepts of motion. In the what we call particle model, it's a qualitative way to represent motion. So here in this diagram, the way you do this, you draw a series of dots, and the dots show a sequence of motion. In this case, so an object would be moving like from this position to here to here. This motion, because the dots are equally spaced, the velocity must be constant. It's maintaining a constant speed because it's covering the same distance per equal intervals of time. Each dot should represent an equal interval of time, and the distance is how far the dots are apart. This situation, the dots are going upward, up an incline, so as we would expect, the dots become less spaced, and therefore the object is slowing down as it rolls up the hill or incline. Position change in position. Position vector is measured from a reference or coordinate system. So here on the right, there's an axis, and you have a arrow showing the distance from the coordinate system and the angle from it. And you could do the same with the other dots. Change in position vector is the difference between final position to the previous position. This is also the word, let me write this down, displacement. Change in position is the same as displacement. Alright, on the right here we have two position vectors. So at time 1, the position of this object is at the tip here. Time 2, the object is right here. And oftentimes when you look at analyzing motion, you want the change in position. So the way you figure that out is you draw your and from another axis, draw your R2 first. Here's my R2, it's drawn as well as I can, and then my R1 to draw the you subtract. So delta R difference equals R2 minus R1. So to draw negative R1, it is instead of going up in the second quadrant, it would be going 180 degrees opposite into the fourth quadrant. So I go to the tip of R2, then draw negative R1, and delta R would be from the origin to the tip of the last vector. I have the definition of velocity. Velocity is change in position over delta t, which is the same as displacement over time interval. Velocity would be the same direction as the change in position. So if we have the change in position here, then the velocity is in that same direction. Now the arrow is not necessarily equal length because it's like apples and oranges. They're not the same thing, but they will be in the same direction. Alright, practice problem. So I made this situation up. If you could follow the last one, you could probably follow this one. When you do to find a change in position vector or a displacement vector, you draw dots at the position what they're at. So there should be a dot here and a dot here. To find the change in position from R1 to R2, you do what I did in the previous page. You draw R2 first, and then you draw the negative of R1. So that would be 180 degrees opposite. Again, this is supposed to be straight. Vectors are straight. It's just hard to draw straight on this with this program. That's negative R1. So the delta R would be from the origin where we started R2 to the end of negative R1. So the change is here. Or you can think of it another way: is we start here, we make a change from here to here, and we end up with R2. Okay. All right. Acceleration, change in velocity. Acceleration is the change in velocity divided by the time interval. Acceleration vector is the same direction as the change in velocity vector, just as with the change in position and velocity. So acceleration, we learned last year, is the rate of change in velocity. And what the point is here is that whatever the change in velocity direction is, acceleration is the same direction. And you can get that from the equation too, because there's no direction for time interval. So if this is a vector, then this vector on the opposite side of the equation should be the same direction. Complete motion diagrams. A complete motion diagram will include a velocity vectors, change in velocity vectors, and acceleration vectors. Alright, draw a complete motion diagram for an object moving in 3 positions as shown. So I'm going to go ahead and draw that. It's drawn for you. We have an object starting at position 1, going to position 2, then ending up at position 3. So I would say the velocity vector would be here, then down to the right. So on the right here, I'll show you the actual drawing. So that's how I drew it. V1 is up and towards 2, and then V2 from there. Then I'm going to show the delta V and a acceleration vector. So V2, then I draw the negative onto the tip of V2. So the negative of this is 180 degrees opposite, like I shown. That's called negative V1. You connect the two, and then the delta V would be attached to the tail of the first vector drawn to the tip of the last vector drawn. That's delta V. So if that's delta V, then acceleration has to be in the same direction. A problem in physics is represented through diagrams, graphs, known and unknown values. The signs of the known and unknown values are determined by the coordinate system and its direction decided upon. Now, in physics, we don't always have to the right is positive, up is positive. So you can adjust your axes to make it more match the situation. So if you're dropping something, you could have the axes being positive down. If you're going up an incline, you could have the axes going along the incline. But you do need to have the signs need to be correct to get the correct solution. So here in this situation, we have an object starting here. So the dots, this is the particle model. And because the arrows, the spacings are getting smaller, that means it is slowing down as it's moving to the right. So let's answer some questions here. So initial position. The initial position, this is the origin. Wherever the x is, that shows a positive. This is the positive side. This must be the negative side. This is 0. So therefore, this initial position is negative. This final position is to the right of 0, so that's positive. Initial velocity, it is moving towards the right or towards the positive, so this must be positive. V1x, it's moving to the right towards the positive. This must be positive. Acceleration, the way you figure that out, well, I'll do it here on this side. I'm going to take these two vectors, this one, and I'm going to draw this vector to show you how we get the A vector. So V1, draw that one first, the final one first, minus. So instead of going to the right, I'm going to go to the left. It's going to be a lot longer than V1. And that is negative VO. So the change is to start from the beginning. So we started here at the tail of the final vector, and we went to the tip of the initial vector. So the change is that way, therefore acceleration is backwards. Does seem odd that you can be moving forward and accelerating backwards, but in this situation you are. And those are the answers that match up with our discussion. Alright, here's a situation where a lead ball is dropped into a lake from a diving board 5 meters above the water. After entering the water, it sinks to the bottom with a constant velocity equal to the velocity with which it hits the water. The ball reaches the bottom 3 seconds after it is released. So you can see the arrows, it's starting up here being dropped, so I could put a little dot meaning it's at rest. These arrows get longer because it's speeding up prior to hitting the water, but once it hits the water it maintains a constant speed. So the arrows would be a constant length. So this is supposed to be it's not drawn really well. So this should be the same length as, say, this one. Okay, so all right. You're supposed to write the kinematic values, knowns and unknowns, in this problem. So this is the motion diagram. I've drawn my axes. Because all the motion is going downward, I'm going to make positive as being downward, as you can see right here. And I'm going to make my starting spot where I initially dropped it. That makes sense to me. That's the zero, the initial spot. So my initial y is 0. My initial velocity, since you're dropping, is 0. My initial time is 0. It falls 5 meters as the problem reads. So y1 is 5. v1 is unknown. We do not know how fast it is. I'm sure you could probably figure it out from last year's information, but just according to kinematics, it's unknown, and T1 is unknown. It's not given in the problem. Then it maintains a constant speed. We don't know the depth of the lake, so this is a question mark. V2 and V1 are equal. V2 and V1 are equal, and T2 equals 3 seconds. Because the ball reaches about after it is released, 3 seconds after. So time from here all the way down to here is 3 seconds. A couple other things you definitely need to be aware of is you need to know your SI units. Basic units, second, meter, kilogram. There's a few others. And then be able to use metric prefixes. We will not spend a lot of time reviewing that. You've probably done that over the last 2 years. So, but you will be responsible for making those calculations. Important ones in this class, just so you know, are milli, kilo, micro, nano, centi. Those are some of the key ones. Then also review your significant figures. You have spent time on that in chemistry. We use those in labs. They also expect you to do that on the AP exam when you graph data to know the rules. Last thing in this slideshow is orders of magnitude. An order of magnitude calculation is one significant figure estimate. Sometimes a number 1 to 9 can be estimated, but often just an exponent. So examples, height of a telephone pole. Well, so is it, let's see, is it 10 to the 0 power, 10 to the first power, meters? We're talking about meters. This is all meters. So it's definitely not a meter tall. Is it about 10 meters? Is it about 100 meters? 100 meters is kind of high. So the order of magnitude would be 10 to the first power. So that's what I have there. Maximum speed of a household fly. So one of those flies that bugs you in the middle of the night when you're trying to sleep or outside. Again, 10 to the 0 meters per second, 10 to the 1 meters per second, 10 to the second meters per second. And we do know that this is equivalent, by the way, to 1. So which one is it closest to? I would think 1 meter per second. It could be 10 to the negative 1, by the way. That would be 0.1 meter per second. I think it goes a little faster than that. So this is completely an estimate, but it's a logical estimate. It's not just random numbers. Average number of hamburgers eaten in a lifetime. Now you might have to do a little math. I think I did that here. Okay, here we go. 1 burger per 3 days. There's 365 days per year, and there's 85 years in average lifetime. So the approximation would be 1 times 10 to the 4th burgers in your lifetime. You probably didn't realize you ate so many burgers. So let's, if each one is a quarter, let's say a quarter to half pounder. So let's do them. So we're talking half of 10 to the 4th over your lifetime. Let's see. So how much weight is that? So it's what, 10,000? So guess what? You eat 5,000 pounds of burger, ground beef during your lifetime. All right.